Good afternoon, everyone. Good afternoon. Are you ready? Hello. Okay. So let me present to you our lecture for this afternoon, no? I hope naka-share screen ako, no? Kita ng kuhan, screen. Aga akong i-share. Hello?
Yes, sir. Makita ra, sir.
Kita na? Kita na ninyo ang akong i-share screen? Na? Hello?
Yes, sir.
Okay. So in this meeting, we're going to discuss this topic, no? Design sa rectangular footing. So last meeting, nahuman naman ang kuano, design sa square footing. Anybody who can answer?
Yes, sir.
Nahuman na natong discuss ang square footing, di ba? Okay, tingog.
Yes, sir.
Hello? Okay, so I hope ka na. Nadungog na?
Yes, sir.
So nahuman na mo tag-discuss sa first topic, no? Katong square footing.
Yes, sir.
Okay. So karon nga meeting ang atong i-discuss kining design sa rectangular footing, no? So ano sa man ta mo gamit og rectangular footing? Now, sometimes when a footing is placed close to the property line, so for example, mo ni siya ang property line o ni diri nga atong column, and if we use a kining square footing, gawas na siya sa kuha, no? Property line. And ang atong mahimo to maintain the footing area, ang atong width mo narrower, ang atong length mo longer. So, yan na. So, mo resulta na siya rectangular footing. Lain sad nga situation kung pananggit ang spacing between two columns are too close, no? Pananglitan kung natay duha ka column nga dool kayo ang ilang kuha, no, location. Ya mo gamit tag square footing, gawas nga ang ilang kuan footing area mag-overlap na no. So mag-overlap ng ilang footing area. So kung ato nimo na ato ni siyang i-narrower ang mga footing. But to compensate for or to maintain the same area, mugawas nga mas longer no ang footing sa usa ka side. So duha ni siya ka example, of course napay lain no, but I think that will be sufficient for now. Nga dunay mga situations nga kinahanglan mo gamit og rectangular footing. Of course, all things being equal, the most economical footing is the square footing. Mao na siya atong first option. Kung gamit lang tayo ng rectangular footing kung di na ta kung natay mga limitations no. For example, ning duha ka situations nga ato kong di-discuss. The column is placed too close to the property line or the two columns are placed close to each other. So in the problem design, a reinforced concrete footing to support a 600 millimeter square tiled column carrying a dead load of 1,800 kilonewton and a live load of 1,800 kilonewton. The weight of the footing is limited to 3 meters. So assume that the allowable soil pressure at service load to be 240 kPa and F sub C prime is 21 and Fy is 414. Okay, so step one, we proportion the footing dimension based on service load condition. So we compute the total column load, which is the sum of the dead load and live load. At least na ining example, no? Live ato we consider, but in later discussion, we will be considering also seismic loadings, no? So we're going to focus na nag-illustrate nato sa pag-design o action loaded na footing. So we have the sum of the dead load and live load. We get 3,600. Then next, we estimate the weight of the footing. For simplicity, we just assume it to be 10% of the column load. And then we compute the total load supported by the soil, which is the sum of the column load plus the weight of the footing. And next, we compute the required footing area by dividing the total load by the allowable soil bearing capacity. No? So we get an area of 16.5 square meters. We try if we can use a square footing. So to determine the dimension of the square footing, we take the square root, in which case we get 4.06 meters. No? So kung gamit ang square footing, this should be the minimum or the required dimension of a site. But however, the problem states that the width of the footing is limited to 3 meters. So we cannot have a wider than 3 meters no, on one direction. So in this case, we use a rectangular footing, then we use the permissible width allowed, 3 meters. Then we calculate the length of the footing, so divide the required footing area by the width. So therefore, we have 3 meter by 5.5 meter na footing. No? Ano siya atong footing dimension. Okay, next, we compute the factored column load. So we multiply dead load and live load by the load factors. Again, take note that in 2015, this is now 1.2 as the factor for live load is 1.6. Then divide that by the actual footing area to obtain the net ultimate upward pressure. So we are going to use the net ultimate upward pressure in designing the footing slab. Okay, so do you have any question for step one? So feel free to raise your question if you have any, no? Then step two, we compute the depth required for beam shear. Now sa doon ay duha ka possible ining critical section for wide beam shear failure, no? Kini diri nga so the distance of the face of the column, no, in the narrow across the narrow side, pwede sa dire, no? The distance across the wide nga side. So between the two, kini siyang sa narrow nga kuan mo ay mas critical, no? Of course, because it is narrower. Okay? So kung doon naman yung beam shield failure, most likely it will occur in this critical section here. Okay? O di atong compute sa PCAS. So solving for the factor shear that will act at this critical section, that will be the net ultimate upward pressure multiplied by this area, no? Ini siya nga area. Yeah. So mo na dire ang calculation, then the shear capacity is V16 square root of sub C prime BD. Then you equate, no, the shear force to the shear capacity to obtain an equation in terms of D. So masolve na to ang D ni ining equation. So we get here an answer of 0.839. Next, we compute the required effective depth to avoid a punching shear failure. So the critical section for punching shear will be at the over 2 distance from the face of the column, no? And that will occur around the column perimeter. So the over 2 dire, the over 2 PCAS, that will make the dimension of the critical section equal to the column dimension plus D. So since the column is square, then 0.6 plus D dire, yung 0.6 plus D sa dire PCAS. So now we solve for the shear force that will act this critical section, no? So that would be the net ultimate upward pressure multiplied by this tributary area, no? Which is the area of this big rectangle minus the area of this square. So we have the calculation here. Then for shear capacity, we have V1/3 square root F sub C prime BOD. But as noted before, no, there are still other, I think, 3 more equations to verify. Okay? Kani kuan na duha equation kinahanglan pa natin i-check. But given the footing dimension and the column dimension, I don't think that the other two will govern in this case, no? But it is good to check. So for shear capacity, we have V1/3 square root M sub C prime BOD, where BO is the perimeter of the critical section, no? So this is a square. So the perimeter is 4 times the length of a side. We have it here, no? So we have the factor shear in terms of D, then the shear capacity in terms of D. So we equate the factor shear to the shear capacity for, that is the criteria for adequacy. Then we'll get an equation in terms of D, no? So masolve na to ang D. So we get 0.729 meters. So ikumparar ni mo dire nga rin 0.839 nga rin siya for beam shear is 0.725. The larger value will govern, no? Thus we adopt 0.839, but we round this off to a more practical value, say 0.85, so 850 mm. So after step 3, we already have the required effective depth, no? From step 1, we have the footing dimension. Step 3, we have the required effective depth. So in step 4, what we're going to do here will be to compute the steel reinforcement. Now, since we have a rectangular footing, then the steel reinforcement will be the same, no? In both directions. Siguro mo sulod. So kung rectangular footing man no, akong balikon dili sila o lahi ang amount, no, so steel required in the long direction, lahi sa short direction. So sa step 4, atong i-compute ang long direction steel. So kasabot na to na long direction steel, ang steel nga parallel sa long side, no? So mo na siya nga steel ang counteract sa bending moment or hindi nga critical section dire, no? So let's compute the moment. It is simply the net ultimate upward pressure multiplied by this area that will give you the resultant force, then multiply that by its moment arm, no, which is half of 2.45. Okay, so we have the calculation here. Then once you have the moment, you have the width and the effective depth, you can compute the steel reinforcement, no? So these are the formulas we get from reinforced concrete design. So RU equals MU over VVD square, distance ratio FI over 0.85 F sub C prime. The required steel ratio rho is 1 over M, quantity 1 minus the square root of 1 minus 2 RU M of Y. So if we substitute values, then we'll get this answer, no, of 0.00395. Then check this against the minimum steel reinforcement ratio required by the code, no, which is computed using these two formulas here, no, 0.25 square root F sub C prime Fy, but not less than 1.4 over. So between ining duha, kani siyang 0.00338 mas dako, no? Nya kana siya ato ikumpara diri. So mas dako ni siya ang kuan row required, and therefore use this value. So kani yung value ito na siyang i-multiply by BD, and we'll get the steel area, no? So after we get that, we choose the bar diameter. So it can be, just try any bar diameter, no? 16, 20, 25 mm, no? So the area of the bar here will be pi over 4 times the square of the bar diameter, and we compute the number of bars by dividing the area required by the area of one bar. So that's 20.6, so we round off to the next higher integer, no? So use 21, 25 mm diameter bars. Okay, kini siya nga mga steel reinforcement is to be distributed equally, no, across this width. Okay. Then we check the spacing. So we have this formula for the spacing. B is the width, then C is the cover, and the number of bars, then D be the bar diameter. So we get 116 mm. So that is between 75 and 200. It's are the desirable range, no, of the spacing. So therefore, it is okay. So again, if the bars are spaced too close, then you increase the bar diameter. If the bar are spaced too wide, too far apart, then you can decrease the bar diameter. Okay, so okay na tanining long direction steel. Ano sa siguro ay gustong mukuhan. Ano ako higin? Sige. Okay, so next we solve for the short direction steel. Now, if the long direction steel are to be equally distributed, no, equally placed across this width, ang atong long direction steel, na siya ay modification regarding sa iyang distribution, no? So dili siya equally distributed across this width, no? Ang reason niya na kay of course ang mas dako nga pressure, if you imagine the bending, no, sa tong footing, mas dako siya stress sa region nga dool sa column. Samtang katong mga region na lain sa column dili na kay to siya mo mas lesser, no, iyang kining effect, no. But the calculation for the required steel area is the total would be the same, no? So, mo ni siyang critical section for moment na to dire. Kumpleto na to pila may bending moment being a critical section. So again, upward pressure times this area gives you the force, multiply sa moment arm, which is 1/2 of 1.2, no? So we have the calculations here. Then we have the moment, we have the width, we have the effective depth, and we can compute the steel reinforcement using the formula we have from reinforced concrete design, no? So RU rho then compared with rho min. So in this case, ang atong rho required ni siya is less than sa rho min na to nga 0.0038. So the code says that when rho required is less than rho min, we may use the smaller between 4/3 rho and rho min. So we multiply 4/3 of rho required to obtain 0.00129. We can use the smaller between this value and this value, no? So we use this value here. Now the absolute minimum for reinforcement should not be less than that required to control temperature and swing gauge, no? Which is 0.0018. So karon mas tuloy mo mas mag-govern na siya, no? So ang atong sa requirements of temperature sa AST, no? That is 0.0018 times BT, no? So not BD but rather BT. Whereas sa kuan, kaning sa flexure, you have rho BD. Okay? So just try to verify which is so I think this one will really govern, no? 0.0018 compared to this. So we should use this value. So 0.0018, so a slight correction here, instead of D, okay, that should be T. Because when we compute thermal reinforcement, it should be multiplied to the thickness rather than the effective depth. Okay? So pila may atong atong compute dire 850, no? So tingali may buong mga anong 825 na siya. So ang rason niya na kay kung mo ni siyang thickness sa footing, this is our long direction steel. We place the short direction steel on top, no, of the long direction steel. So that effective depth will be 1 bar diameter less, no, than that in the long direction. So more ni siyang effective depth na to sa short direction, whereas the effective depth for the long direction calculation na siya, no? So that is 1 bar diameter less. But again, as I already noted, no, so instead of 825, just make this correction here, no? O kani siya, kay temperature man may govern, no? Use the thickness. Rather than the effective weight. So ang thickness na to will be 850. So in this case, ang atong arena na ito swap, no? So thickness will be effective depth 850 plus maybe 100 mm cover. So we'll get 950 millimeters. So mo na siya ang gamiton, no? Instead of 825, we should use 950. Okay? So kani siya nga amount sa steel reinforcement, ato na siya dili na nato siya equal spacing, no, across the short direction. Dili we place more bars at the center strip or the middle strip, and the remaining bars we distribute equally in each of the outer strips. So ang pangutan na pila may atong ibutang sa middle strip, pila ibutang sa outer strip. So mao ni siya ang proportion, no? So first, ano siya nga formula? So AS1, that is the amount of steel reinforcement to be placed in the middle strip. Then that is in a proportion 2 over beta plus 1 multiplied by the area required, no? The total area required. So kaning beta, that is the aspect ratio, which is the ratio of the long side to the short side of the footing. So we get 1.83, substitute there, then we get for the middle strip required amount of reinforcement in 5,772. So ang sunod na yan, pila may buta mahibilin para sa outer strips, no? So we take the difference ni ini nga value, kini nga value dire, no? Then we divide by 2. Okay? Katunga dire pikas. So we get this result. So next we compute or rather we select the bar diameter. So in this case, we just choose 20 mm diameter. This is the area of the bar, and we compute the required number of bars, no, for the middle strip and for each of the outer strips. So sa middle strip 18. Anyway, diri 3.82 atong gi-round off to 4, 18.4 pwede na lang ang iyo na to 80 na lang na. No? Pwede sa 90, no? Anyway, naman kay gipuno diri, pwede sa kamukuha diri, no? And we check the spacing. So the spacing is critical at the middle strip where you have more bars, no? So nga rin natin mag-check sa middle strip. D is the width of the middle strip and cover. C is the protecting cover, then N the number of bars, DB the diameter of the bar. So we get here 146 mm. So it is between 75 and 200 mm, which are the desirable range, no? So spacing. So okay na siya. Then next we check the development length. So ang atong development length, I don't know if I have drawn here. Ngari lang, no? So kani siya nga distance, no? Ikan diri paingon diha. Is the available nga development length. So that is 1.2 meter multiplied by the cover. So mo ni diri ang atong LD provided, no? Ani siya 1,200 minus 75 nga cover, we get 1125. Then compare this with the required development length, no? So mo ni siya ang atong mga formula for computing the required development length. So kani siya ang unang formula, kani siya ang ikaduha nga formula, then ikatulo kani siya ang minimum, no? Okay, so naa kay kani siya mga development length factors. So alpha sa ganito ning alpha is the I think location factor, then beta is the epoxy coating factor, and then Y, let's look at the definition for this one. I forgot the definition of this. Let's bring it down. Okay, so na alpha is the reinforcement location factor. So this is not top bar, and therefore we have 1.0. Then beta coating factor, there is no epoxy coating, so 1.0 sa dang anyway, beta 1.2, no? Does the problem specify that we have epoxy coating? It does not, no? So magamit ito 1.2 for all other epoxy coated bars. Kung uncoated ang reinforcement, dapat 1.0 na siya. So try to change that one. This should be, instead of 1.2, that should be 1.0. Okay? Huwag man tayo epoxy coating. That's 1.0 for uncoated bars. And Y is reinforcement size factor. So we are using what reinforcement? Ang diameter ng atong gamit is 20 mm, no? So, kung 20 mm, then so may atong gamit. I think 20 mm, no? So kini dire, okay, tira 20 mm, no? Atong gamit. So kung atong ang tanawon dire, it should be 0.8 for 20 mm diameter and smaller, and 1.0 for 25 mm diameter and larger. So therefore, kanidi ay 1.0, no? delete ni siya dapat 0.8 ni siya. 0.8 for 20 mm diameter and small. Okay, yata ni siyang lambda lightweight aggregate concrete factor. So normal weight man is okay, 1.0, that's correct. So just try to make the necessary correction here. Beta, change that to 1.0, and kaning Y, change that to 0.8 instead of 1.0. No? Okay, so I think that's fine. Now, for dowels, that is optional since we embed all the column rebars into the footing. So don't worry, don't bother about that one. Step 6, we check the weight of the footing. So we have the thickness of the footing is effective depth plus 100 mm cover. So 950, then we can compute the volume and multiply that by the unit weight of concrete to get the weight. So in this case, ang atong actual weight is 368. Ang atong assumed weight from step 1 was 360 kilonewton, no? So ang atong actual weight was dako kay sa assumed weight. So ang atong buhaton na balik tang ito sa step 1, i-recalculate na to, no? Because the weight of the footing is heavier than assumed. Pero gamay ra magdiferensya, no? 368, 360, and just take that as okay. And we should remember, no, kaning allowable pressure na to nga gihatag nga 240 kilopascal. Kani siya nga value. This is a very approximate nga value, no? Factor of safety na 3.0. So whether you have actually 368 or 360, a difference of 8 kilonewton, it's not really significant, no? Percentage wise ni mo ni gamay ra kay na siya nga percentage difference. Don't bother, no? Okay. Sa structural design, di ko na to, dili na siya kinahanglan 0-0 gid ka kanunay, no? There is room for kining mga approximation, no? Then finally, we draw the detail. Ang kuan dere, no? Muna siya ang sectional view. Then we have here the plan view. So ang importante, balik ko na to, no? Kinahanglan imong iutang diyang mga information nga gikinahanglan aron ma-construct, no? Ang footing according to your intention, no? As the designer. So diri sa atong detail na diri ang thickness, na ang footing dimension, na ang steel reinforcement, no? So diri na kay 21 25 diameter distributed equally. Diri nga kuan na kay 18 of 20 distributed equally, and on the outer strips you have 4 of 20 mm diameter also distributed equally, no? So yung na, no? So I think this topic is not difficult, no? Wala siya mga sayong nga topic, kining isolated square o isolated nga rectangular footing. Okay, so that's it. Nabay mga pangutana? Back to you. Any questions? So I hope that you are already reading the lessons in advance, no? Since you've already the lecture notes, pwede na mo mag-advance o study, no? Tingali, karon nga week, no, I'm trying to post the plate problems. So you can also already start solving. Any questions? How about the others? Kayang-kaya, no?
Hi, sir. Can I clarify lang, sir, sa load combination, sir, ba?
Saman.
For the plate problem, sir, kay will we be using, like, follow lang may sa book, sir, nga katong factored load combinations ng 1.4 and 1.7, sir. Not na katong USD, sir.
So ang atong i-follow sa plate katong NSCP to 2015, no? Ang mga load factors. Kaya kanang 1.4, 1.7 karaan na kayo na siya.
Okay, sir.
We don't
Thank you,
use
sir.
that anymore. We use the recent, no? Mga load factors nga gi-recommend sa code. 1.4, 1.7 will give you an overly conservative nga design. So, kung gamito ng bago, no, at least mas economical lang atong mga design.
Thank you, sir.
Okay. So, na ba yung question? So, by the way, on Wednesday, we're going to have a face-to-face class. May mga ganyan tani nga kada klase, face-to-face ang kagpirmay. No? So, kung may go signal ang university, no? 100% face-to-face. Ito na ning tunga-tungaon, no? I want to discuss the more difficult ng mga kuan face-to-face. Because for me, there is very little interaction in online na class. Kaya itong face-to-face kaya naagad nagatubang kita. No? So, what else? Is there other concerns? May bang mga kuha niya nga gusto ninyong ipaabot? O okay na mo? Okay, so kung walang pangutana, then we can end the class early, no? It's still 4:20, but we're supposed to end 4:30. But sa iyo man tamahuman karon, no? Mubor man ang atong topic. So, okay na ta. So kung wala questions, then you are dismissed. Sige, ayo-ayo.
Thank you, sir.
Sir.
Thank you,
Thank
sir.
you,
Bye,
sir.
sir.